Welcome to Part B of Unit 1 for our course on statistics, and I am just about ready to introduce to you an equation, a very special equation. In fact, it will be an equation that we will essentially spend this entire course on. We're going to build on this equation and expand on it in many different ways, but essentially our entire class will be about this one very special equation. And I'm going to show you that equation in just a moment. But first, before I do, I need to make sure you're clear on the formula for a mean. And so that's what I have on this page here. So say, for example, I have a group of something. It could be a group of people or a group of frogs or a group of potato plants. I don't know, whatever it is. But in this case, it looks like I have a group of people on this page here. And so it would be a sample. So a group of something, I have a sample. And then I assess every case in the sample on a variable. So everybody has a score on a variable. For example, I'm recording this at the time of the pandemic. And in my own research, one variable I've been looking at is the extent to which people feel concerned or anxious about the ongoing pandemic. So say I did that with this sample. So I had this sample of people, and everyone in the sample took my questionnaire. It has several questions on it that measure the extent to which they feel concerned or anxious about the pandemic. And then those questions are summed together to get a total score. So every person has a single score on my questionnaire measuring the extent to which they're concerned or anxious about the pandemic. And I'm going to call that variable X. So everybody has a score on variable X. For example, that's their score indicating how much they feel anxious or concerned about the pandemic. And so we can use that then to calculate the mean. So recall a mean is just another word for the average. So the mean for my group is the same thing as saying the average for my group. And what I have down here is the formula we're going to use to calculate a mean. And I'll use the symbol X bar, and X with a bar on top of it will be the symbol for a mean. That's the mean for variable X. So if I call my variable X, then X with a bar over it is the symbol for the mean of variable X. And that mean of X is equal to the sum of all the individual X variables, and this Greek capital sigma sign, that's the summation sign. That means to sum everything that comes after that symbol. So I have my summation sign, that Greek capital sigma, and then that's next to the X, so that means to sum all the individual X values. So for every single person, I take their score on X and I sum all those together to get everyone's scores together. And then I'm going to divide that by N. And in statistics, we will use the letter N to indicate the size of the sample. So if I have a sample of 50 people, then N is 50. If I have a sample of 80 people, then N is 80. So N is the symbol we use for the size of our sample. So taken together, our formula for the mean, that is the average, we say X bar, the mean, is equal to the sum of all the X variables divided by N, and that will give us the mean for X, or the average of X. And I have a note on the right here that sometimes we might call a variable X, and usually if I have just one variable in a study, I call it X. But we'll be doing a lot of things in this class where we look at studies where we have two variables, an X variable and a Y variable. And usually if I have two variables, it's common to call one X and the other Y. So another version of this formula, if I had a variable I called Y instead of X, is to say Y bar, so now I use the letter Y and put a bar over it, is equal to the sum of all the Y variable scores divided by N. So we could write it with an X or a Y. We could actually use any letter if we wanted to, but X and Y are the two most common letters to use to assign to variable names. And if I have just one variable, we will usually use the letter X. So that's the formula for a mean. Now that we have our formula for the mean, I want to pull one single person out of the sample, and I want to ask a question about that one person. So say I pull just one person out of the sample, and I'm going to call this individual I. I could stand for individual, or we could call this case I. That's going to be just a single person that I pull out of the sample. So say I pull this person out of the sample. Well, actually, that's a picture of me. I wasn't really in that, but let's pretend I was part of that group. And I kind of tried to Photoshop myself in there just a bit. So I pull one single person out of the sample, and I'm going to call that single person case I. And of course, case I, because case I is a member of that sample, and every single person was assessed for their score on variable X, say how concerned they were about the pandemic. So case I will have a score on variable X. Every single person in my sample has a score on variable X. And so if I pull just one person out of that sample and call that case I will have a score on variable X. So now let's consider this question. What if xi is unknown? That is, I don't know what this person's score is on variable X. But say I do know what the mean is. Say I've calculated the mean for the entire group, and maybe the mean for my entire group on how concerned they are about the pandemic, maybe on a scale that goes from 1 to 10, maybe the average is an 8, for example. So say we discovered that the average is equal to 8. And then I pull this one single case out of the sample and say at this point, I don't know what this person's score is on that variable. I don't know how concerned this person is about the pandemic. So if we know that the mean is equal to 8, but if xi is unknown, we don't know the value for the single case, what is the best prediction of xi for this case? In this scenario, if I said, I had a competition here and a bunch of people were going to guess what they thought the score was for case I, and whoever comes closest to case I's actual true score, you're going to win $1,000 or something like that. What would be the best guess you could make for the score for case I? So the question is, what is the best prediction of the score for xi if you know what the true mean is, but you don't know what this person's score actually is? In other words, what is the guess that will make the least error? If you want to come as close as possible to that person's actual score, and maybe I could do a game like this: the closer you get to that person's actual score, the more money I give you. So if you come with just a half a point away, you get $1,000, but if you're a few points off, then you only get $100 or something like that. So the closer you get to that person's score, the more money you make. So what would be the best guess you would give for that person's score? So what would it be? And if you think about it, the answer is 8. The mean is 8. The best guess for that person's score would be the sample mean. And this seems like a fairly simple thing, but this is going to be a very important concept. That the best prediction we have for the single score for case I, if I don't know what that person's score actually is, but I do know the mean, well then the mean is the best prediction I can make for what that person's score is. And now I'm ready to show to you that very special equation that I was talking about. And here it is. It's the equation you're looking at right now on the screen. And when you look at this, it might look like a fairly simple looking equation, but it's something that's going to do quite a lot of wonderful things for us. And we're going to be expanding on and building on this equation throughout this entire course. So what do we have here? We have a letter X with a little pointy thing on top, and I call this pointy thing a hat. And a hat means it's a predicted value. So an X with a hat on top of it means the predicted value for variable X. Or if I had a letter Y with a hat on top, that would indicate the predicted value for variable Y. And then I have a subscript, a letter I down here, to indicate I'm talking about just a single case that I pulled out from my sample, and I'm going to call that case I. So what I have on the left-hand side here, X hat subscript I, it means the predicted score for a single person from my sample who is case I, the predicted score for case I. And this equation says the predicted score for case I is equal to the sample mean. And that's what we were just looking at just a moment ago, the fact that if I don't know someone's score on a variable, but I do know the sample mean, well then the sample mean is my best prediction, the best guess I can make for what that person's score might be if I don't know what that person's score is. Now, one thing that's going to make this equation especially useful to us is that it's an equation trying to understand people's predicted scores. I'm trying to predict what should someone's score be on variable X? And in research, that's essentially what research is all about. Research is actually all about trying to predict outcomes to things. That is, so for example, if I do a treatment study where I have a treatment group and a control group, and maybe it's a treatment for anxiety, if my treatment's effective, then if I know if you receive the treatment or not, I could predict your level of anxiety. If I have a highly effective treatment, I could predict if you receive the treatment, you won't feel anxious. But if you're anxious and you don't get my treatment, you'll probably be high on anxiety. So the better my treatment works, the better I can predict what your outcome will be after receiving my treatment. Or if I understand what are the causes that cause people to experience anxiety, then if I knew your score on those causal variables, I could predict how anxious you would feel. Or if I was doing a correlational study, if I knew the extent to which two variables were correlated, if I knew your score on one variable, I could predict your score on the other variable. So we can think of research, essentially all of research boils down to this. We're trying to get information that will allow us to make predictions. And when we get bigger effects, when we get amazing results from studies and we get bigger effects and we discover things, that will allow us to increase the accuracy of our predictions. So we can think of research as being something where it's all about trying to predict outcomes. The more we know, the more we understand, the more we learn, that the better we could predict outcomes based on the information we have. And what we have here in this equation, it's a starting point. If I don't have any other information, well then the sample mean is just the best prediction of someone's score. Now what we're going to be doing throughout this course is we're going to be saying, well, what if I have more information? What if I know if this person was in a treatment group or control group? What if I know something about this person's thought process or this person's personality, or if I have scores on other variables, how much will that increase my prediction? And so we're going to be looking at questions of, well, this equation shows us what we would predict if I didn't have any information other than the sample mean. And then we'll start asking questions, well, what if I have more information? How much better does my prediction get? So that's part of the reason why this equation is going to be so important for us. And one thing to note here is that I've labeled this as a linear equation. And if you're familiar with what linear equations look like, you might look at this equation and say, well, this doesn't really look like a linear equation. But later on in this course, it will become apparent. It will look more like a linear equation as we begin to add things to this. So if it doesn't look exactly like a linear equation right now, trust me, eventually we will show you how this really is a linear equation. So here it is. This is the equation that our entire course will really be all about. This equation. We're starting with this foundational equation. X hat for case I is equal to the sample mean. And now we're ready for our first song. So in this course, there will be several places where I will want you to give me definitions of important terms. And when you give me these definitions, I will want you to be able to highlight the most important thing to know about each term. And to help you learn these definitions, I've put together some songs, and each song has lyrics that define an important term and that highlight the most important thing to know about that term. So if I ask you to give me the definition of one of these terms, one option you have is simply to give me the lyrics to the song that define that term. Or, if you prefer, you can give me a definition in your own words that highlights the most important things to know about that term. So, here is the song, The Mean, that gives us a definition for the mean and highlights the most important things to know about the mean. So, what's the most important thing to know about a mean? Well, that's what we were just talking about. That's the fact that the mean gives us a predicted score or an expected value. That is, if I have a sample of people and I pick someone at random out of that sample of people, and I want to guess what their score is on variable X. I don't know what their score is on X, and I want to make the best possible prediction I can to predict their score on X. I want to make the prediction that will make the least amount of error in guessing what their score is. Well, in that case, my best bet is simply to guess the mean. If I want to bet the mean is a score I would expect to get. That's the person's predicted value. That's a score, my best guess for what I would expect to get. If I don't know that person's score, I would guess the mean. So the lyrics to the song are, if you pick someone at random and you want to bet The mean is a score you expect to get. And I'll play the song for you. And by the way, if you want to hear it by itself too, these songs are also at the Saibu website. I have stat music there, and if you want to see the song by itself, you can go to the website and just listen to the song. But I'll play it for you now. And when I play it, what I recommend you try doing, maybe I'll sing it through a few times in the video, and maybe the first time listen to how it goes, and then see if you can sing along with it, and then see if before I'm done you can sing along without looking at the words. So here is the song, The Mean.
Well, if you pick someone at random and you wanna bet, the mean is the score you expect to get. 'Cause if you pick someone at random and you wanna bet, the mean is the score you'd expect to get. 'Cause if you pick someone at random and you wanna bet, the mean is the score you'd expect to get. 'Cause if you pick someone at random and you wanna bet, the mean is the score you'd expect to get.
So let's review what we've done so far. We started off with this equation for a mean, for the mean of variable x. And then I said, what if I pick someone at random from the sample? I pick one person out. I pick out a single case, and we'll call this case I. So I have a single person or a single case, which is case I, and I want to predict or guess what that person's score is on variable x. Now, I don't know what that person's score is on variable x, but I do know what the sample mean is. And so what we've been talking about is, in this situation, the mean is my best guess. It's my best bet. It's my best guess for what that person's score is. Like the song said, if you pick someone at random and you want to bet, the mean is the score you'd expect to get. And so that leads us to our equation, this very special equation we've been looking at, that says a person's predicted score on variable x is simply equal to the sample mean. Case I's predicted score on variable x is equal to the sample mean. Now, I want to ask you this question. Is there some way we could rearrange or rewrite this main equation in a way that takes away the hat? Can we take away that hat? How do we need to rearrange this equation if we take away the hat? Because right now, with the hat, we have an equation that's equal to a person's predicted score on variable x. But what if I want to change it so it's an equation that is equal to a person's actual score, their real score on variable x, case I's actual score on x? I want to take away this hat to have something that's equal to the person's actual score. So how would I rearrange this equation so that I take away the hat? Well, here is an equation that takes away the hat. So here's that exact same equation. This is the same equation, the one I'll call a linear equation. The equation our class will be all about is right here. And it's the same equation we've been looking at. I've just rewritten it in a way that takes away the hat. So now instead of x hat on the left-hand side of the equation, x hat was a person's predicted score. I've taken away the hat. So now I say the actual score on x for case I is equal to the sample mean plus e for case I, and E will stand for error. That's how much mistake I make when I use the mean to predict that person's score. So I'm saying that person's actual score, case I's actual score on variable x, is equal to the sample mean plus error for case I. That is the amount of error that I make when I use the mean to predict case I's score. So I could write my equation one way to say x hat is equal to x bar, or I could say x for case I is equal to x bar plus e. That is the error for case I. So those are two different ways we can write the exact same equation. And this slide is just clarifying the terms for this equation without the hat. So x sub I, or x for individual I, is the score on x for case I. X bar is the mean for x, or it's the mean of all the xi scores. And E sub I, that's the error for individual I, that's the error for case I. And that's how far case I deviates from the mean. So if I use the mean to predict the score for individual I, the amount of error that I make is simply how far that case deviates from the mean. So the error is the amount of mistake that I make when I use the mean to predict someone's score. And another way to say the same thing is the error is simply how far that case deviates from the mean. Now, one thing that's good to keep in mind in looking at this equation is note that the components that have a subscript I, these are things that could be different for every single person in the sample. So if I have a group of people here, every single person can have a different score on X. And what that means is every single person will have a different amount of error, but there'll be just one mean for my entire sample. So there'll be one mean. Every single person can have a different score on X. And so when I use that mean to predict their scores on X, it's possible that every single person can have a different amount of error. Some people might be the same, but they don't have to be. It's possible that every single person can be different. Let's look at a visual illustration to show what I'm talking about here. So say, for example, I have a sample of babies here. What do I have? 1, 2, 3, 4. I've got 6 babies. And let's say I'm measuring something about these babies. Maybe I'm measuring how much they drool. And so I have this first baby here is a baby named Keith. And Keith drooled 15 units. I'm not sure, maybe 15 ounces or something. That'd be a lot of drool, I guess. But let's say ounces. So Keith drooled 15 ounces, and I have this graph here, and they're not, the babies aren't in any particular order going from left to right, but I have, here's baby Keith, and here's 15 on my graph right here, so I put a dot right here, and I have an X to say the X score, I should have put an XI there to say it's XI for baby Keith. So Keith drooled 15 ounces, so X for baby Keith is 15, and then here's baby Gerbert, and Gerbert drooled 30 ounces, so I have down here X equals 30 for Gerbert. And then here's Rufus, and Rufus only drooled 5 ounces, so I got X equals 5 for Rufus. And then here's Bruno, and he drooled 25 ounces, so X equals 25. And the key thing to note here, as I'm drawing all this out, is that every single case, in this case every single baby, has a different score for X. Keith has his score on X, Gerbert has her or his score on X, and Rufus has his score on X, and so forth. Every baby has its own score on variable X. Now, if I take these scores and calculate the mean, the average of these scores, just sum them all up and then divide by 6, I get a mean of 20 in the sample of 6 babies. The average amount of drool is 20. And I drew a red line right at the mean. So there's a red line going right across here. That's exactly at the 20 ounce mark. I drew that red line going across there to show that the mean is 20. And note there's only one mean. Every single baby had its own unique X score, but there's just one mean for the entire sample. And now we can look at the errors. Or actually, let's start off, let's look at the predicted values, and then we'll look at errors. So note that each baby is going to have its own predicted score, but in this case, we're going to predict the same thing for every single baby. Later on in this class, we'll be doing things where we'll start predicting different things for different cases. But right now, we're just using the mean to predict everybody's score. And so for every single baby, for every single case, they have the exact same predicted value. So we look at Keith here, the sample mean is 20. So if I didn't know Keith's score on X, my best prediction is simply to guess the sample mean, which is 20. So the predicted score for Keith is 20. And here's Gerbert. If I don't know Gerbert's actual score, my best prediction for Gerbert's score is the sample mean, which is 20. And so every single baby has its own predicted score. Every single baby has its own X hat. But in this case, we're just using the mean to predict everyone's score. So actually, every single baby has the same predicted score, even though each baby has its own predicted score. So if I have 6 babies, I have 6 X hats. Each baby has its own predicted score. Now, let's look at the errors. So the errors is simply the distance between the observed and predicted score. If I take someone's observed score minus that case's predicted score, that would give me the error. So here's Keith, and Keith's predicted score was 20, right at the sample mean there. But Keith actually scored a 15. And so if we take Keith's observed score of 15 minus the predicted score of 20, 15 minus 20 gives us -5. So the error for Keith is -5. And here's Gerbert. Again, we predict 20 because we're predicting 20. 20 is a predicted score for every single baby in the sample, so we predict 20. But Gerbert actually drooled 30 ounces. That was 10 units above what we predicted, so the error for Gerbert is equal to 10. And then here's Rufus. Rufus only drooled 5 ounces, but again, our predicted score is 20, so observed minus predicted, 5 minus 20 gives us -15. So Rufus's error is -15. So for every case, we take that case's observed score minus the case's predicted score. Observed minus predicted, that is their actual score minus the predicted score, gives us the error. And again, note that every single baby has its own error. So Keith has a score for error. Here's the error for Keith, -5, and Gerbert has an error of 10, and Rufus has an error of -15, and Bruna has an error of 5, and Eep has an error of 15, and Ooze has an error of -10. Some rather interesting names there. So the key thing to note is that every single case has its own score on X, and every single case has its own predicted score, although in this example, the predicted scores are the same for every case, and every single case has its own error, although there's only one mean for the entire sample. So here is the equation we've been working with. We have the score on X for individual I is equal to the mean on X for our entire sample, plus the error for individual I. And the error is how far individual I deviates away from the mean. That is, the error is the amount of mistake that we make when we use the mean to predict scores for individual I. And we saw how every single case in our sample will have its own error. It will have its own deviation. And now let's consider a couple important questions about this error. So what is the average deviation of all the errors in our sample? And what is the average deviation of all the absolute errors? When I put two lines on either side of my error like that, that means the absolute value. That is, the values if I take away negative signs, so all the values are positive. What is the average absolute deviation of my errors? Let's go back to that previous picture just to clarify what I'm asking here. So here's my sample of babies, and every single baby has its own error. So Keith was a -5, Gerbert was 10, -15, and so forth. So the first question is simply, what is the average of all 6 of these errors? And you could answer that question by calculating it. We could take -5 plus 10 plus -15 plus 5 plus 15 plus -10, add it up, divide by 6, and calculate the average. But you wouldn't need to do any calculation because the average of the errors will always equal 0. That will always be true. In fact, the sum of the errors will always be 0. In this case, for example, you've got -5 plus 10 plus -15 plus 5 plus 15 plus -10. If you add that up, you get 0. And that will always be true. That will be true because the mean is always a balancing point. You will always have the exact same amount of error above the mean that you have below the mean, because the mean is a balancing point. So that means the sum of the deviations, that is the sum of the errors, will always add up to 0. So the average of the errors will be 0. Now, that other question is, what if you take absolute values? What if I scribble out these negative signs and take +5 plus 10 plus +15 plus 5 plus 15 plus +10? What if I take absolute values and calculate the average of those absolute values? I'll go back to that page we were just looking at. That's these, the absolute values of our errors? What is the average absolute values of the errors? And I ask that question because I want to lead to these other questions is, well, if we calculated that, what would that tell us? Why would this be important? Can you think about why it might be important to know the average deviation of our absolute errors, the average absolute deviation of our errors? It turns out one reason is that the average absolute deviation of our errors will turn out to be important for measuring things, and we'll see how that will be true in just a moment. But there's another reason why this could be important that might be a little bit more obvious to you at the current point in time. So recall that our errors are telling us the average amount of the amount of mistake that we make when I use the mean and nothing else to predict people's scores. So the average of my absolute errors is saying, on average, how much mistake do I make when I use the mean and nothing else to predict people's scores? And what we're going to be doing in this class later on is we're going to start using other information to predict people's scores. And hopefully, when we use other variables, other information from other variables to try to predict people's scores, hopefully our predictions will improve. And if our predictions improve, we'll start making less error. Our mistakes will be smaller. And so we can make a comparison. What is the amount of mistake that we make when I use the mean and nothing else to predict someone's score? And then later on, we'll be asking, well, what is the amount of mistake we make if I use the mean plus other information to try to predict people's scores? Do I make less error? Do my predictions get better? And we'll use this to address that question. So to know the average deviation of our absolute errors will be very, very important, and we'll be coming back to that throughout this class. So I've got a second question here is, well, how do we calculate it? We could just simply take the average of our absolute deviations. That's what I've been talking about. And that's what I'm illustrating here on this slide. So I have the absolute deviations, the absolute errors for each baby in the sample. That is, I've taken away the negative signs. So the absolute error, the absolute deviation for Keith is 5. And the absolute error, the absolute deviation for Gerbert is 10. And for Rufus, it's 15, and 5 for Bruno, and so forth. So I've taken away the negative signs. So I now have absolute values, that is, absolute errors or absolute deviations. We could use either term. And if I just sum these up, I could add up all these absolute deviation values. And so take 5 plus 10 plus 15 plus 5 plus 15 plus 10, add them up, divide by 6, and I would get an average deviation of 10. So 10 units, that tells me on average how much mistake do I make when I use the mean to predict each baby's score. That is, what is the average deviation from the mean? And we could use this method of calculation when we want to know on average how much do scores deviate from the mean. But we're not going to do that. We're going to do something a little bit fancier. I suppose this is a statistics class, and statistics is supposed to be hard and difficult and challenging and impressive when you tell people about the things you learn in statistics. And if we just say, well, we just took our average absolute deviations, added them up, and divided by our sample size, that's a little bit too simplistic. Couldn't we have a more fancy, a more fun, more complex method of calculating these average deviations? And indeed, that's what we're going to do. We're going to calculate something called the standard deviation. And if you've had stats before, hopefully you recall what a standard deviation is, or at least recall calculating one. Sometimes people calculate standard deviations and they forget why or what they're doing. And one thing that's important to know is that I'm about to tell you how to calculate a standard deviation, but before I do, keep in mind that the standard deviation is simply going to answer this question. It's simply going to be a different way of calculating the average absolute deviation. It's what we calculate if we want to know, on average, how far our scores deviating from the mean. It's the thing we calculate if you want to know, on average, how much mistake do I make if I use the mean to predict everyone's score. We calculate the standard deviation. And it's just a fancy, complex way of calculating the average absolute size of our deviations. That's all it's giving us. But we need to make a few adjustments and a few fancy little tweaks to address a few issues as we go along the way here. So, if I wanted to know the average absolute size that people deviate from the mean, if we use this method here, conceptually this is right. This is giving us what we want to know, but it wouldn't be the correct answer. There's a few problems with it here. Now, the difference between this method and the standard deviation is going to be sometimes not that big, and there might be some cases where if you use this method, you might be close enough to the actual standard deviation that it would be counted correct, but it might not be. So this method right here, we're not actually going to do this. Conceptually, this is what we want to know, but this isn't the actual method we're going to use. So let's look at how we would actually go about calculating this thing called a standard deviation, and it will give us information of what is the average deviation for our sample. And here is the first step to calculating a standard deviation. What I'm going to do is to take all my deviation scores, and rather than taking absolute values of those deviations, I'm going to square them. That is, rather than simply taking away the negative signs, I'm going to take each deviation score and square it. And that will have the same effect, because if I have a negative value and I square it, that will give me a positive value. So I'm going to take all my deviations and square them. Here's the first case is, I think that was Keith, and he was, his drool was 5 units below the mean, so his deviation score was at -5. His actual observed drool was 5 points below the predicted value, below the mean. So his error was -5, his deviation was -5. And so I square that and I get 25. And the next baby was 10 points above the mean, 10 points above the predicted value. So I take 10 and square it, and I get 100. And I take the next deviation score and I square it. So I take each deviation score and I square it. And then what I'm going to do is I'm going to add up all these total squared deviations. So I take 25 plus 100 plus 225 plus 25 plus 225 and so forth. I take all my deviation scores, my squared deviations, and I add them up, and I'm going to call that my sum of squares. And in this particular example, our sum of squares is equal to 700. So the sum of squares is the sum of our squared deviation scores. Now, you might be wondering at this point, why am I squaring my deviations rather than simply taking the absolute values? Which would be a very good thing to wonder. It would be sensible to wonder that. Now, if I just wanted to know the answer to the question, what is the average size of the deviations? That is, I wanted to know, on average, what is the amount of mistake that I make when I use the mean to predict people's scores? If that's all I wanted to know, then it would make sense simply to take absolute values of my deviations and to calculate a standard deviation based on absolute values. But the thing is, when I calculate a standard deviation based on squared values rather than absolute values, it's kind of like, well, it's kind of like sprinkling fairy dust on my formula. It's like it turns my formula into something magical. That is, I can take this standard deviation if I've used squared values in my formula, and I can plug it into other formulas and it will do important things. And we're actually going to be doing that later on in this course. There's going to be other formulas we're going to be using in this class. And in many of these formulas, a standard deviation will be a component of that formula. And if we calculate our standard deviation using squared values, it makes all these other formulas work. And if we were to calculate a standard deviation using absolute values, then all these other formulas would stop working. It's kind of like when we use squared values rather than absolute values. It's like we flick on a light switch that makes everything light up, and all these other formulas start combining with the standard deviation and they start working in ways we want them to work. So the reason why we need to use squared values rather than absolute values is so that we get a formula that will do more than simply tell us what's the size of the average deviation, but we get a formula that can also be plugged into other formulas and make everything work. So that is the sums of squares. What do we do next to calculate a standard deviation? What's our next step? So now that we have our sum of squares, you might think that the next step would be to divide that sum of squares by the number of people in our sample. given that our goal is to get an average deviation, or now we have a squared deviation. So if we want to get an average squared deviation, you would think we would simply take our sum of squares and divide it by the number of people in our sample. But once again, our formula is going to take a bit of a twist here, and we're going to do something fancy. We're going to do something a little different. So instead of dividing by n, so the letter n, that's the letter we use to indicate our sample size, we're going to divide by n minus 1. So in our sample here, we had a total of 6 people in our sample. So our n is equal to 6, n minus 1 is equal to 5. So I will take our sum of squares, 700, and I'm going to divide that by n minus 1, our sample size minus 1, and that'll be 700 divided by 5, so I get 140. And I'm going to give this value a special name. I'm going to call this my variance. So the variance is anytime I calculate my sum of squares and divide by n minus 1, I'm going to call that my variance. Now, when I divide by n minus 1, I give that a special name. I call that the degrees of freedom. So n minus 1 is called the degrees of freedom. And taken together, this probably raises 2 questions. The first question is, what do I mean by degrees of freedom? And the second question is, why do we divide our sum of squares by our degrees of freedom? Why don't we simply divide by our sample size? Why do we divide by degrees of freedom? So let's take a look at those 2 questions. First, what do I mean by degrees of freedom? Why do I say n minus 1 is called degrees of freedom? So to explain what I mean by degrees of freedom, I would like to play a little game. And hopefully by the time we're done playing this game, you will understand what degrees of freedom means. So say I have a sample of 4 people here. I've got 4 people. I think these are all musician types of people here. And maybe, how about I say I do a study where I let these people listen to my song about the mean. And I ask them to rate how much they like that song on a scale of, say, 1 to 10, where 1 is they really don't like the song, and 10 is they really, really love that song. So each person in my sample is asked to listen to my song about the mean and rate how much they like it. And so the game goes like this. Here's the first person in our sample, and she's going to rate how much she likes my song on a scale of 1 to 10. And the question is this: what does her score have to be? What does her score have to be? And at this point, you might have a puzzled look on your face. And if you have a puzzled look on your face and you're thinking, what? Well, it could be anything. I don't know what her score has to be. Well, you'd be right. We don't know. Her score could be anything. It doesn't have to be anything. We don't know what it is. So let's say, for example, her score turns out to be a 4. She likes it kind of a little bit less than a 5, so a little bit moderately likes it. So her score is a 4. Let's look at the next person and ask this question: what does her score have to be? Again, you kind of might give me a puzzled look and think, well, it could be anything. I don't know what it is. And you would be right. We don't know what her score has to be. Her score could be anything. So say, for example, she got a score of 7. She kind of liked the song. Next person, what does her score have to be? And once again, well, we don't know. It could be anything. I don't know. It doesn't have to be anything. Maybe her score is a 3. She didn't care for it all that much. And then final person in our sample, what does his score have to be? Well, again, it could be anything. We don't know. You're probably beginning to think, what's the point to all of this? Well, hold on. There'll be a point to this eventually. So what does his score have to be? Well, we don't know. Say, for example, it turns out to be a 6. So now at this point, if we've collected data for all 4 people in our sample, we've got a 4, a 7, a 3, and a 6, we could calculate the mean. And I just did that right up here. So the mean, 4 plus 7 plus 3 plus 6, add that together, divided by 4, we get a mean of 5. So the average score in the sample is a 5. So now that we've calculated our mean, let's play our game again, but this time we're going to be playing our game after we have calculated the mean, and we know that the mean is 5. So if the mean is 5, and we do a study, we don't know what anyone's score is at this point, we know the mean is 5, what does her score have to be? Well, it could be anything. It's free to vary. We don't know what it is. So once again, maybe her score is a 4. Next person, what does her score have to be? Well, it could be anything. We don't know. If the mean is 5, this person received a score. She could receive anything. We don't know what it is. And say, for example, she received a 7. Okay. Next person, what does her score have to be? Our third person right here, what does that score have to be? If the mean is a 5 and the first person got a 4, the second person got a 7, what does her score have to be? Well, it could be anything. Her score is free to vary. So say, for example, her score is a 3. But now, at this point, if the mean is 5 and the first person got a 4 and the second person got a 7 and the third person got a 3, what does his score have to be? Well, this final person's score is no longer free to vary. We say we have lost 1 degree of freedom. If the mean is 5 and we know the scores for the first 3 participants, our final participant, that person has a score that is not free to vary. His score will have to be a 6 to make it work out. So what we do is we say once we calculate a mean, we have lost 1 degree of freedom. Once we calculate a mean, there is 1 score in the sample that is no longer free to vary. So we lose 1 degree of freedom. So that's why when I say degrees of freedom, that means the size of my sample minus 1. In the size of my sample minus 1, I call that degrees of freedom. Oftentimes we abbreviate that with a letter D and F. DF stands for degrees of freedom, and degrees of freedom is my sample size minus 1, in minus 1. And that's because once I calculate a mean, I lose 1 degree of freedom. So whenever I calculate a mean, I lose 1 degree of freedom, and my degrees of freedom becomes n minus 1. So now we see that when I say our formula for the variance, we take our sum of squares and divide by n minus 1. That's the same thing as saying we take our sum of squares and divide by degrees of freedom, because degrees of freedom are equal to n minus 1. Now, that still leaves the question, why in the world do we divide by degrees of freedom? Why don't we simply divide by our sample size? Well, that has to do with something called bias. And the thing is that if we divide our sum of squares by our actual sample size, we will have a biased statistic. And if we divide by degrees of freedom, we will have an unbiased statistic. But I'm not sure how much that clarifies things, because I think I've just raised another question. Okay, what in the world do I mean by bias? When I say I have a biased statistic, what do I mean? And in this case, I'm not using bias in the way we usually talk about bias. Oftentimes, when someone says someone is biased, you might say someone has a negative attitude or a negative opinion or is prejudging someone. And that's not what I'm talking about here. In statistics, we use the word bias, and the word bias means something a little bit different. So, we need to give a definition of bias. And to give a definition of bias, I need to give a definition of one more thing. We keep on getting more and more things we have to define here. But before I can define bias, I need to define something called the expected value of a statistic. So let me first define what an expected value of a statistic is, and then we can define bias. So we've talked before about how we can have a population, which is all the cases that we want to make a claim about. So if I want to make a claim about all the people in the world, then my population is all the people in the world. And how I draw a sample from that population, a subset of that population, are the people I include in my study. And I could calculate a statistic, which is a numerical value derived from that sample. It could be an inferential statistic. It could be a descriptive statistic. Say, for example, we're talking about means here. Say I just get my sample and I calculate a mean, an x-bar for my sample. That would be a descriptive statistic about my sample. So I could draw a sample from the population and calculate my mean. Now, let's say I replicate my study over and over again many times and calculate a mean each time. That's what's depicted in the upper right-hand corner of our screen over here. It's supposed to depict a situation where, say I get a sample of 30 people and maybe I have all of them listen to my my song about the mean and rate how much they like my song about the mean. And I get my sample of 30 people. Here's my first sample, and get their X bar, their rating for how much they like my, and maybe their mean is equal to a 6. And then I get my second sample. I'm going to get another sample of 30 people and get their mean, but maybe they like it a little bit less. On average, maybe that sample is equal to, maybe their mean is equal to a 5. And then I'm going to replicate my study again. I get another sample of 30 people and calculate the mean for that sample. And maybe they like it, maybe they really like it more. Maybe their mean is 7. And I'm going to do this again and again. So imagine I were to do this an infinite number of times. An infinite number of times, I go to my population, I draw a random sample of 30 people, and then I have them rate how much they like my song, and I calculate the mean. And then I do that again. I get another sample of 30 people and calculate the mean for that sample. And then I get another sample of 30 people and calculate the mean for that sample. And I do that an infinite number of times. And each time I replicate my study, I'm probably going to get a slightly different mean. I'm probably not going to get the exact same value every time I replicate my study. So now what I have in this pink area up here, this is supposed to be, imagine I did this in infinite number. I only have 6 samples here. That's all the space I had. But imagine I actually had an infinite number of samples in there. And each time I had a sample, I took that sample from the population and I calculated a mean. So I actually have an infinite number of means from all the infinite samples that I collected from my population. Of course, I couldn't really do this in real life, but imagine that I did. And so now I have this pool of all these means from all these studies I did, and if I calculate the average of all those means, that average, I'm going to call that the expected value for my mean. That's the expected value for my statistic. Here, let me give you a formal definition of what I mean by expected value. So the expected value is the average of all the values in a population of values from which a single value can be randomly sampled. So in other words, we have this population of values, all these means from these. If I replicate my study over and over again an infinite number of times, I have this population of means from all my studies. And the expected value is the average of all those means. And this is a situation where I have this pool of all these means, and I could randomly draw one study from this population and see what the mean is from that study. And if I think about it, maybe I do a study where I do go and get a sample of 30 people and have them rate how much they like my song. And here's the study I actually did. Say I have one study that I actually did. Here, this down here, this will be my study. I actually did this study. Say I actually went and got 30 people and had them rate how much they like my song and got the mean. And maybe in my study, the mean was equal to, maybe it was 5.5 or something like that. So that is the statistic that I got in my study. Then I can say, well, what was the expected value for the statistic in my study? The expected value for the statistic in my study would be the average that I would have gotten. So the expected value is not something we can actually know, but we could say hypothetically, what would that expected value be? Hypothetically, if I could do replicate my study an infinite number of times and calculate the average of all those studies, that would be the expected value, the value I expect to get when I do my single study. So it's the average of all the values in a population of values from which a single value could be randomly sampled. And if I randomly sample one single thing from this population, the expected value for that single thing is the average of all the things in that population. So that's what an expected value is. And so at this point, I want to talk about the expected value of a statistic. That is, if I replicate a study over and over again an infinite number of times, and each time I calculate a statistic, the expected value for that statistic is the average of all the studies that I've done. So we can now define the term bias. And when I use the word bias or the word unbiased, I'm talking about a property of a statistical formula. Statistical formulas can be either biased formulas or unbiased formulas. And a biased formula is a formula where the expected value for a statistic is different from the true population parameter, And an unbiased formula is a formula where the expected value is the same as the population parameter. For example, we've been talking about the mean, and the mean is an unbiased statistic. That is the formula for the mean, where we sum all the values on x and then divide by our sample size. That formula produces the mean, and that formula is unbiased, meaning that the mean is an unbiased statistic. So if we were to have a population, say we were going to calculate the mean for how much people like my song about the mean. And I have maybe the population is all the people in the world, and I draw a sample of 30 people and calculate the average for how much they like my song. And then I replicate my study, get another sample of 30 people, calculate how much they like my song on average, get another sample of 30 people and calculate their mean. And so now I have this infinite pool. I replicate my study over and over again an infinite number of times, and I have all the means from all those infinite number of replications of my study, and I can calculate the average of those means. And if the average of my means, actually I might do like a mean with a double bar, so the mean of the means, two bars on top of that, the mean of the means, say the mean of the means is 6. That is the average of all these values in the pink area when I replicate my study over and over again an infinite number of times. If the mean of those statistical values is 6, well, then I know that the true population parameter will also be 6, the mean of everybody in the entire population. We'll be talking about this later, but actually when you give the term for the mean of the entire population, we often use the Greek letter mu, which looks kind of like a letter U a little bit. That's supposed to be the Greek letter mu there. But if the expected value was 6, then the true population parameter would be 6. And this would be true for a mean, because a mean is an unbiased statistic. So anytime, and this is something that statisticians could use formulas to prove that this is true. And if we wanted to spend time doing this, we could delve into the workings of how the mean functions, and we could actually prove and show that this is true, that the expected value for a mean, if we were to replicate a study over and over again an infinite number of times and take the average of all of our means, that expected value would be the same identical value as the mean of the entire population. The expected value will equal the population parameter. And that's simply a mathematical property of the formula for the mean. And so we say the mean is an unbiased statistic. But if we had a statistic where the expected value was different from the true population parameter, we would call that a biased statistic. And so that brings us back to our formula for the standard deviation. So like I was saying, we calculate this thing called a variance, where we take our sum of squares and we divide by our degrees of freedom. And the reason why we divide by degrees of freedom and not our total sample size is that if we divided by our total sample size, our formula would produce a biased statistic. If we divided by our total sample size, we would get a good idea of the average squared deviation in our sample. But if we were trying to use this to estimate the true population parameter, we would consistently slightly underestimate the true size of the standard deviation in the population. So if we divide by our total sample size rather than degrees of freedom, we will end up with a biased statistic. We would end up with a formula for a standard deviation that would consistently underestimate the true size of the standard deviation in the entire population. So if we divide by our total sample size, it would probably give us a good reflection of what we are actually observing in our sample we're looking at. It would describe our sample pretty well, but it would be biased if we're trying to estimate the true population parameter. And one important property of a statistic is that we would like to use unbiased statistics. So we will always calculate our variance by taking the sum of squares and dividing by degrees of freedom, because that produces an unbiased estimate of our standard deviation. And so like I was saying, we have a sum of squares, we divide by degrees of freedom. In this sample, we got a variance of 140. And the sum of squares divided by degrees of freedom is something we will call that the variance. And I'm going to use that word frequently in this class. And oftentimes when I use the word variance, this is what I'm talking about, the sums of squares divided by degrees of freedom. There's actually going to be many places in this class where we'll need to use a variance, and we will plug this formula for a variance in many places. And this is actually the key formula, that because it's based on squared values, it has many special properties that make it do things for us in many other formulas. And if it was based on absolute values, it wouldn't work so well. So this formula for the variance, sums of squares divided by degrees of freedom, gives us something we call the variance, and we're going to use this quite a bit. And this is a value that will be a bigger value when you have bigger deviations, when scores are more spread out from the mean. The bigger the deviations you have, the bigger your variance is going to be. And the smaller the deviations, the more scores are close to the mean, the smaller your variance will be. So your variance reflects the extent to which scores are spread out. The variance reflects the size of the deviations in your sample. That is, the variance expresses the amount of mistake that you make if you use the mean to predict everyone's score. But the one thing about a variance that makes it not too easy to interpret is the fact that it's based on squared deviation. So in this case, we say our variance is 140, so the average squared deviation is 140. But we don't often think in terms of squared values. So if I want to have a value that's meaningful and easy to interpret, just to say, okay, what's the average size of the deviations here? I want to unsquare that value. Well, I suppose the appropriate mathematical term for unsquaring something is we take the square root. So if my variance is 140, to get the thing I'm going to call my standard deviation, I simply take the square root of my variance. So I take the square root of 140 and I get 11.83. And recall that when I just took the average of the absolute deviations, that got me an average deviation of 10. And that's probably a good way to describe the size of the average deviations in the sample, but my officially calculated standard deviation is 11.83. It's a little bit larger. And actually, if the sample was large, we have a fairly small sample here. If I had a much larger sample, if I had 30 people or 50 people, the difference between the two formulas would be more subtle. And if you had a very large sample, it could be almost a negligible difference between the two formulas. But here we have, but we can see that our formula using the appropriate method with our degrees of freedom here, we get 11.83, which is a little bit larger estimate. And that's because if we had just used the absolute values and if we had just divided by sample size rather than n-1, we would have slightly underestimated the true population parameter, and we would have had a formula for a variance that didn't have these magical properties that allows it to be plugged into other formulas. So the official formula for the standard deviation, if we want to know on average how far are people deviating from the mean, that is, on average, if I use the mean to predict everyone's score, on average, how much mistake do I make? That average deviation, that average error, that average amount of mistake in this sample is 11.83. That's our standard deviation. Sums of squares divided by degrees of freedom, then take the square root, and that's my standard deviation. And now that you have a conceptual understanding of sum of squares, variance, and standard deviation, you should be able to write out the formulas for these values. So at the top we have the formula for sum of squares. And we'll use the letters SS to indicate sum of squares. And we'll say SS, sum of squares, is equal to the sum of, there's that Greek capital sigma that we use as the summation sign. So the sum of, and then we put in parentheses, x of I, that is the score on x for individual I, minus the mean, minus x bar. So that we get the deviation here, xi minus x bar. That's the deviation score for individual I. And then we square it to get the squared deviation. And then we're going to sum that for every single person in our sample. So taken together, our formula for sum of squares is the sum of x of I minus x bar squared. And that will give us our sum of squares. And then to go to our variance, we simply take that sum of squares formula, take this formula right here, and I'm just going to take that exact same, I'm going to put our sum of squares formula right there in the numerator, and then have a denominator where I divide the sum of squares by my degrees of freedom, which is n-1. And then to get my standard deviation, I take the formula for my variance, I take this whole formula right here, and I just plug it down right here, and I just take the square root of that whole thing. So I just take the square root of my variance, and that will give me my standard deviation. And I will use the letters SD to indicate a standard deviation. So my SD stands for standard deviation. And because the standard deviation is simply the square root of the variance, we can go back the other way. The variance is simply the square of my standard deviation. So if I give you a variance and say, what's the standard deviation? You simply take the square root. If I give you a standard deviation and say, what's the variance? You simply square it. So because a variance is simply a squared standard deviation, the symbol for a variance is SD squared. SD squared is our symbol for a variance because a variance is simply a squared standard deviation. So those are the formulas for sum of squares, variance, and standard deviation. And that brings us to another song. Here is the song for a standard deviation, with lyrics that give a definition for the standard deviation and highlight the most important things to know about the standard deviation. So in the song, there's two key things that are important to know about a standard deviation. One of them is something we've been talking about, and another thing is something we haven't talked about a whole lot yet. So I have the lyrics here. The standard deviation is used to measure things. It's how far the average person strays from the mean. So the second line of that song, that's what we've been talking about. The standard deviation tells us how far on average do people deviate from the mean. And of course, there's many ways to say that. We could say, how far on average do people deviate from the mean? Or if we use the mean to predict people's scores, on average, how much mistake do we make? That's two ways of saying the same thing. Or the song says, how far the average person strays from the mean. So that's what a standard deviation tells us. And then the first line of the song is that the standard deviation is used to measure things. And I haven't talked about that a whole lot yet. But that's what we're going to see after this point. We're going to look at the ways that we can use the standard deviation to measure things. We might be able to make somewhat of an analogy to the idea of a light year in physics. So in physics, they've calculated what is the distance that light travels in a year. And then once they've calculated that distance and they know what that distance is, they can use light year as a measurement. They can say how far away is a star in light year units. They can measure distance between stars in light year units. And a light year units is a distance that light travels in a year. So we can do something kind of similar in statistics. We can figure out the standard deviation, which is the average distance that a person strays from the mean. And once we know that distance, we can start measuring things in standard deviation units. And this is actually going to be a key thing we're going to do to answer those questions when we want to know how big something is. If we want to know if someone's score is a high score or a low score, being able to measure things in standard deviation units will help us do that. If we get a result from a study and we get an effect and we want to know, is this a big effect or a small effect, we actually can use the standard deviation to help measure things to determine whether our effects are big effects or small effects. So one of the key things you're going to see in the upcoming units we'll be looking at is that the standard deviation is very important because we use it for measuring things. So the two important things to know about the standard deviation in my definition here. The standard deviation, it's used to measure things. And conceptually, what is it? Well, it's how far the average person strays from the mean. So I'll play this song for you, and as before, my suggestion is see if you can, maybe the first time through, listen and hear how it goes, and then see if you can sing along, and then see if you can sing along without looking at the words before the song ends. And so here is the song for the standard deviation. And that is everything for Part B of Unit 1.